I'm going to give you an example of how we would show that an estimate is unbiased. And I think that this will help solidify this concept in your head. So what we'll do first is we'll talk about how, in general terms, we're just going to outline the basic steps to figure out if an estimate is unbiased, and then we'll run through that example. Please note that only estimates can be biased. All right? There's no way that a parameter can be biased. Remember, a parameter is a statistic calculated on the entire population. So there's no way, if we go back to the definition of what biased and unbiased means, it's saying that the estimate is biased. For example, the estimate is biased when there's a consistent tendency to either overestimate the parameter or underestimate the parameter. But a parameter can't be biased because it's not an estimate. So whatever you calculate, it is what it is. It can't be biased. It's always unbiased, right? It's always unbiased because you have everybody in the calculation. Okay, so how do we find out if an estimate is unbiased or not? Well, there are three basic steps. First one is you have to exhaustively sample. And I'm going to define what that means in a minute. But I'll tell you what it doesn't mean. It doesn't mean that you sample and sample and sample and sample until you're so exhausted you can't move on. That is not what this means, okay? So that's one thing. Okay, step two, you calculate the estimate in question. So if you're estimating mu, you're going to calculate x bar. All right. If you're trying to estimate variance, then you're going to calculate s squared. So whatever it is you're trying to estimate, you're going to have to calculate that for every sample that you get. Step three is find the mean of those estimates. Those estimates that you just got are just numbers, right? So find the mean of those numbers. Now, if the mean of your estimates, so the estimates are just numbers, maybe they're sample means, maybe they're variances, s squares, but whatever it is that you are estimating, those are just numbers. If the mean of those numbers is identical to the parameter that we're estimating, then the estimate is unbiased. All right? So let's run through an example here. First, a little bit of jargon. All right, so we've already said that if we get all of our estimates and we calculate the mean of those estimates, as long as this mean is equal to the parameter, the corresponding parameter, we know our estimate is unbiased. So if, let's say we're estimating x bars, not estimating x bars, we're estimating mu. So we're calculating a whole bunch of x bars, right? Because x bars estimate mu. So if we've got a ton of x bars and we take the mean of those numbers, if that mean equals mu, right, the parameter, mu, then it's we know x bar is unbiased. If instead, let's say we're trying to estimate variance in the population, sigma squared. So that's our parameter, sigma squared. So we're going to calculate a whole bunch of s squares. If the mean of those s squares is equal to sigma squared, then we know that s squared is unbiased. All right. The jargon is this is how we write it. The expected value of our estimate equals the parameter. Okay, so E stands for expected, and then here you put it whatever it is you're estimating, and then the parameter. So if we were trying to show that x bar is unbiased, x bar would go in the parentheses because that's the estimate. So x bar would go here. What parameter is it estimating? It's estimating mu, so you would put mu here. and then don't forget to put the E in front. Okay, so that would mean that the expected value of X bar equals mu. That's how we would write it. And we would say if this is true, then that makes X bar unbiased. Okay. If we were trying to estimate the parameter sigma squared, then we would put S squared here because S squared is the estimate. Sigma squared is the parameter. And then we would say the expected value of S squared equals sigma squared. Because if this statement were true, we would say that S squared is unbiased. As long as the expected value of S squared equals sigma squared, it makes S squared unbiased. Okay, you might have to play this over and over again just to make sure you got it. Okay, now remember the first step is to exhaustively sample, right? And I'm going to define that in a minute. But I want you to know, just because we exhaustively sample does not mean that our estimate will be unbiased. That's just the first step in figuring out if something is unbiased or not. All right, so just because you did it, well, yay, congratulations, but you still have to do step 2 and 3 to determine if your estimate is unbiased. Okay? All right, let's run through an example. I think it will really kind of set this home. Okay, so the first step is to exhaustively sample, right? So what is exhaustive sampling? To exhaustively sample means that we take all possible different combinations of a given sample size from the population. All right, so take all possible samples for a specific sample size, get all the different samples possible from that population, but each sample has to be a different or unique combination of numbers. So let's look at an example. Let's pretend you have this population, 2, 3, 4, and 7. Well, we can work with that, right? That's only 4 numbers, so that's not a big deal. Here's our population. Now we have to choose a sample size. Remember, we have a given sample size. So we're going to choose a sample size of 2, and that's why I have this here, thing 1 and thing 2. So that means that every sample we take from this population has to have just 2 numbers in it. So let's do that. Let's find out what all the different possible combinations are when we have sample size of 2. So you could get a 2 and a 3 in your first sample, right? I mean, that's possible. Could be 2 and 3. Now, the next time you sample, maybe you're going to get 2 and 4. And then the next time you sample from your population up here, you might get 2 and 7. And then you might get 3 and 4, 3 and 7, 4 and 7. All right, now these are all the unique combinations we can get from this population. That's it. We have exhaustively sampled. If we were to go back and try and get another one, it would be a repeat of what we already have. Now, some of you are probably saying, but wait a minute, we don't have 3 and 2 here. Well, yes, we do, because it doesn't matter which order the numbers appear in. It's like somebody asking me, how many children do you have and who are they? And I say, I have 2 children, Burgess and Troy. Oh, but wait a minute. No, I really have 4 because I have Troy and Burgess as well. All right. So you can only count them once. Burgess and Troy is the same thing as Troy and Burgess. I don't have 4 kids just by switching the numbers around. Okay. So when we exhaustively sample, we don't care about what order they appear in. We're interested in the unique combination, which means order doesn't matter. So these are all the unique combinations. These would be duplicates. So how many unique samples did we have? 1, 2, 3, 4, 5, 6. So we only have 6 unique samples. we have now exhaustively sampled. Now, there's a reason why I didn't give you a larger population here, because when we see populations get bigger and bigger, so does the number of unique samples grow. In fact, it grows exponentially. So even if I had a population of 10, you think, oh, that's really small, right? Population of 10. But to take all possible combinations of 2 at a time, that would take hours probably for us to figure out, okay? So we're always going to, use very, very small populations to show this to you. Okay, so now we've exhaustively sampled. Now let's run through the remaining steps, and I'm going to prove to you that X bar is unbiased. In other words, I am going to show you that the expected value of X bar does in fact equal mu. Remember, as long as we can say that this statement is true, we know that X bar is unbiased. So here we go. We have our population, 1, 2, 3, 4. I'm going to calculate the mean of this population, which is pretty easy to do. You just have to add up these 4 numbers, and that equals 10. Divide by 4 gives you 2.5. Okay, so this is mu. And we're going to select a sample size of 2. I'm going to keep it really simple here. First step, remember, is exhaustively sample. So what are all the possible combinations of 2 numbers that I can get when I sample? Well, I might get a 1 and a 2, a 1 and a 3, that's possible, 1 and 4, 2 and 3, 2 and 4, 3 and 4. Now, have I exhaustively sampled? Well, you can try this on your own at home. Try and find another unique sample, and I guarantee you, you won't be able to do it. These are all the unique combinations. Okay, these are all the unique combinations possible when you take 2 at a time from this population. If you go back and try and get another one, I guarantee you it's going to be a repeat. Maybe the order will be different. Maybe you're going to get a 2 and a 1. But remember, that doesn't matter. Okay, so whether the order in which they appear doesn't matter. So a 2 and a 1 would be the same thing as a 1 and a 2. All right, now that we have all of our unique samples, the next step is to calculate the mean of each sample. So because we're trying to prove that X bar is unbiased, so that means we calculate the mean. If we were trying to prove that S squared is unbiased, so the variance of the sample, S squared, then we wouldn't be calculating mean here. We would be calculating S squared. So you'd have to calculate the variance of the sample and then put the number here. The variance of this sample and put the number here. Okay, so what goes here depends on what you're trying to prove. If you're trying to prove that X bar is unbiased, then X bar goes here and you calculate all the means. If you're trying to prove that S squared is unbiased, then S squared goes here and you calculate the variance of every sample. Okay, so going back to X bar, because that's what we're trying to prove, right? So the mean of 1 and 3 is 1.5. The mean of, did I say 1 and 3? 1 and 2. The mean of 1 and 2 is 1.5. The mean of 1 and 3 is 2. The mean of 1 and 4 is 2.5, etc. Now, if we calculate the mean of these numbers, it should equal mu. All right, so let's do that. Let's take all of these numbers and calculate the mean. So what we have to do is we have to add them all up, and that's shown here. So we're adding up all of these numbers, and then there were 6 of them, so we have to divide by 6. When you do that, you get 2.5. Look at this, 2.5 and 2.5. The mean of all of our X bars is the same thing as mu. that shows you that X bar is unbiased. All right, now that's going to be true from now until the cows come home. Once we show that, for example, in this case, X bar, once anybody shows that X bar is unbiased, that's true forever and ever and ever, unless the Earth starts spinning in the opposite direction. Okay, so a long time ago, somebody figured out that X bar was unbiased. That is true for you. If I end up teaching your children someday, it's going to be true for them. And I'm kind of hoping that I never teach your grandchildren, because that would make me really, really, really old. Okay? But it still will be true for them. X bar is unbiased. We know this. We figured it out. It's always going to be unbiased. Now, we put here as a symbol the mean of the means. And the reason why we're using mu here, all right, and this is a little sub X bar. This is like telling us what we're calculating the mean of. So the mean and then sub X bar means mean of the means. The reason why we're using mu is because, remember, if we exhaustively sample, we have all the samples that we can get that are unique from the population. So when we have all of anything, it's considered a population. So we can put mu here, okay? The mean of all these means is equal to the mean in the population. Now again, if we were trying to prove that S squared is unbiased, then we would calculate the mean of all the S squares. Remember that this number here is whatever you're trying to prove up here. So if this is S squared, that makes this S squared, and then you would write the mean of all the S squares is equal to what? It's not going to be mu, because what is S squared estimating? Sigma squared. So you would have to put sigma squared here. All right? Now, this is not a mathematical proof, because some of you can say, well, you've just shown it for one specific data set. How do we know that this is always going to be true? And the answer is, go to the math department, right, and have them show you the mathematical proof for this. I don't know if I ever knew the mathematical proof. I think when I was learning statistics, my stats professor just told me this is always going to be true, and I believed him. So, you know, maybe it's not true. My stats professor was lying. I'm kidding. I guarantee you this is true, okay?